Okay, welcome to episode 2 of the Calculus playlist, where we are going to begin our discussion of differentiation. Probably the easier of the two between differentiation and integration. So we're probably going to spend the first 8 or so episodes just on this. So first of all, we need to do something called defining differentiation from first principles. So first principles isn't just a calculus term, it's a general mathematical term meaning to prove something from its base, from its logical starting point. Why did we end up inventing this in the first place? Well, calculus and differentiation and all the stuff, or most of the stuff you're going to learn, was invented several hundred years ago by Isaac Newton, the gravity guy, or by Leibniz, a German mathematician, depending on who you ask. They both did it around the same time. And the reason that they both came up with this idea of calculus was because they wanted to answer the question, very simplistically, how can I find a very exact expression for the gradient of this curve here? Well, up until this point, what you've probably done is drawn a tangent at this point, drawn a nice straight line, calculated a gradient of that line and approximated that to wherever you're working with. But that's just not really good enough. So what Newton, Leibniz and anyone else attempting this realized was we can take any 2 points on this graph, and this is a graph of f of x, okay? So it's a function graph. We're not going to use y anymore. We're going to use f of x. And we can take any 2 points A and B. Now A, I'm going to say, has an x coordinate of x naught. So the initial x coordinate is going to be x naught. And I'm going to say that B has an x coordinate of x naught plus h, okay? X naught plus h. This is just general, so I've got a distance between these 2 points of h. Now, the y coordinate of A, well, to write this out professionally, it will be the function when x is equal to x naught, which is just f of x naught. Similarly, the y coordinate of B is going to be the function when x is equal to x naught plus h. So, all I've done is I've defined the coordinates of A and B. A has coordinates x naught, comma, f of x naught, and B has coordinates x naught plus h, comma, f of x naught plus h. Now, what we note is if I were to draw a straight line, that'll do, a straight line between A and B, and I were to calculate the gradient of this line between A and B, how would I do that? Well, for a straight line, my gradient is the change in y over the change in x. Change in y over change in x. Hopefully we know that. So, what's my change in y? Well, my change in y between A and B is going to be B's y value, because it's higher up, minus A's y value, because it's lower down. What's B's y value? Well, it is f of x naught plus h, minus what's A's y value? It is f of x naught. Divided by change in x. And my change in x is going to be my x coordinate of B, because it's further to the right, minus the x coordinate of A. X naught plus h minus x naught is just h, which remember is what we defined h as. It is this distance here. So the gradient of this line here is f of x naught plus h minus f of x naught over h. Now, I know what you might be thinking. This gradient looks nothing like this curve. if I found the gradient of this line, it's not exactly the gradient of this curve, is it? And you'd be correct, it's not. However, something interesting happens as I start to move B down this curve. So, if B isn't up here and it's instead, let's say here, and I draw another straight line, oh dear, let's try that again. Another straight line, I do, between my new B and A. It's still not exactly there, but it is actually closer to what the graph looks like. Just a little bit closer. And because of the way I've defined things, the coordinates of B here are still x0 plus h and f of x0 plus h, because I haven't actually said any numbers. x0 is staying fixed, I'm not changing that. H is always the distance between them, so my coordinates of B haven't changed, and the gradient of my green line is still this. I just have to put in all my different numbers later. Well then, what if my B moves even closer? Well, if my B moves down here, it's almost like my straight line between them is lying directly on the line. There's a little gap, but it's close. I'm just going to draw this a little bit bigger over here because I'm running out of room. The closer that A and B get to each other, the closer the line that connects them simply looks like the curve. If I put A and B right next to each other, then the straight line between them is just going to lie on the curve. There's going to be not much delay, or not much distance between them. So, we can write this in a rather professional way. What we're really saying there is h is getting smaller and smaller and smaller. We want to get A and B as close as possible to try and eliminate this approximation. We don't want it to be approximate, we want it to be correct. But it's only going to be correct when h hits 0. But h can never hit 0, because if it does, my gradient of the line I've drawn is going to be divided by 0. And I can never divide by 0, so that's not going to cut it. So what I do is I state lim, meaning the limits, meaning my number is continuously changing as h goes towards 0. And this little thing here is telling me that in an ideal world, h would be 0. I want h to be 0, I want them to be close together. H is getting closer and closer to 0, but I'm never going to hit it. I can't have h as 0, otherwise the maths just breaks. So I'm instead saying the limits as h tends to 0. As h gets closer and closer and closer to 0, but doesn't quite hit it, then my gradient works. F of x0 plus h minus f of x0 divided by h. And what we've got here is my definition of differentiation. It is taking a general gradient, just a change in y over change in x, between 2 points, and it is squishing these points together as close and close as possible as h gets closer and closer to 0. And this here is my definition of differentiation from first principles, from just logically looking at a graph and calculating gradients. So that does it for this one. So all we've really done is defining differentiation. It's very, very important. Every function from here on out that we differentiate, I will show you how to do it, the snazzier, easier way, but also I will make a point of putting it into this formula. Because if you put everything into this formula, it always works. It's just not necessarily very easy.